Hello, this is David. Let's take a look at John Hull's chapter on interest rates. We have several learning objectives in this chapter, and I would also add it's just a really important chapter in the FRM Part 1, if not in finance generally, because interest rates play such an important role. If nothing else, you'll notice that the risk-free rate shows up in so many of the quantitative or calculated problems that we especially want to be familiar here with this third learning objective. Convert interest rates based on different compound frequencies. It shows up here third on the list, but I just want to highlight this third learning objective. You really want to be comfortable with this. In fact, you want to master this. So important. More on this very shortly. But we start with some definitions. We're following the chapter, and Hull introduces to us different rates. After all, there's no such thing as one interest rate. There are different interest rates. A treasury rate is the rate an investor earns on treasury bills and treasury bonds. That's a government borrowing in its own currency. I highlighted that because I don't know about you, but when I hear treasury rate, I think of the U.S. treasury rate. And that's maybe the most common rate, but it's not the only treasury rate. A treasury rate is any government borrowing in its own currency, and oftentimes it's a proxy for the risk-free rate on the theory that a government isn't going to default. Now that's less assumed after the crisis than it was before. Then we have LIBOR, London Interbank Offer Rate. Very common rate, controversial after there was a well-publicized crisis associated with LIBOR and traders actually manipulating LIBOR because it's the result, or the actual number is determined by a survey of major banks. So in fact, 18 global banks are surveyed, and then based on that survey, LIBOR is determined. But for our purposes, the key point about it is here, it's an unsecured wholesale deposit rate between banks and tends to be short term. We have repo rates. In contrast to LIBOR, repo rates are secured rates. So this is a secured lending rate. We have Bank A, which may be entering the repo, sells security and borrows the cash with the promise that it's going to pay the cash back to get the securities returned. So a repo is a secured lending rate, and the repo rate is the difference between the selling price today and the repurchase price later. That gives us the interest paid on the loan, and because it's secured, the idea is that there's very little credit risk. We have this notion of the risk-free rate, and really since the crisis, there's been a lot of literature and studies devoted to this concept of what is the risk-free rate, how do we measure it? Well, because prior to the crisis, LIBOR rate is used for the short-term risk-free rate, and that's a double A-rated financial institution borrowing rate, again unsecured. Since the crisis, you'll see in John Hull, and this is more true in the 10th edition where he fully fleshes this out and actually makes the substitution, but the overnight indexed swap rate he argues, ought to be the risk-free rate. So that's the OIS. And treasury rates are tempting to use because, again, they're government borrowing rates, and we tend to assume that governments won't default. So it intuitively makes sense to reach for the treasury rate as a risk-free rate. But as John Hull notes, there's three problems with that. These three problems contribute to the fact that the treasury rate tends to be artificially too low. The first is market demand. If we think about supply and demand economics, more demand is going to lower the price of money or borrowing. The regulatory relief, because these treasury instruments help with capital relief and from a regulatory perspective, and also favorable tax treatment. These three factors, according to Hull, make Treasury rates too low to be used accurately as the risk-free rate. Then we get to this learning objective. Calculate the value of an investment using different compound frequencies. And so now we're at this concept of compound frequency, as I suggested. I just think this is a very fundamental skill. It might be boring, but you really do want to master it. If for no other reason than mastery will make some of the more difficult concepts easier later on. So Hull starts with this equality here. You really should study this until it makes sense to you, but if we take an amount, A is some amount of principal today, on the left here of this equality, we compound this at a continuous rate over n number of years. And it could be equal to, on the right, taking that same amount and compounding it at this time at a discrete rate. So a discrete rate is any non-continuous rate. It could be annual, semi-annual, monthly, quarterly, daily. Those are all discrete rates. M is the number of compound periods per year. So if it's a semi-annual rate, M equals 2. If it's a quarterly rate, M equals 4. And so here we have the same N again, it's the number of years. But if we're going to use a semi-annual rate, we need to divide that per annum rate by 2 and then double and then multiply the number of years by 2 so we have twice as many compound periods. But if these are equal, dividing out or canceling out the A, we have a mechanism here to translate from a continuous rate to its discrete equivalent, and from a discrete rate to its continuous equivalent. So it's fine to look at these and watch me explain this, but I can tell you right now, the only way to get mastery here is to practice this with lots of examples. And so here, just from the learning spreadsheet, recall my Excel icon denotes the idea that this is straight from our learning spreadsheets. And here we just have the impact of compound frequency. This is a popular exercise in finance, so I doubt this is the first time you've seen it. But if we have an initial value of 100 and our stated rate is 10% per annum, and by the way, that's how we expressed interest rates. It's very rare that we deviate that. Interest rates are expressed, including in exam questions, as per annum. So this is 10% per annum. I don't have the per annum here, but unless otherwise specified, that's the assumption. Further, it's a stated or nominal rate, 10% per annum, meaning it's actually not quite specific enough for us. We need to know the compound frequency. So you will see, for example, and this would be a typical Hull expression, something like 10% per annum with continuous compounding, or 10% per annum with semi-annual compounding. We actually need that full description for the rate to be specific.